Good evening, good morning and good afternoon. A very warm welcome to our first plenary session. This session is a very special session. This contains a special lecture called First I.I.Sc. 7ICRAGEE Distinguished Lecture, which will be given by Professor Stokoi. Formal introduction will be given by our chair and co-chairs, and the other lecture would be given by Professor Adrian. And we are very thankful to both of them. This is a really odd time for our distinguished speakers, but they kindly accepted and delivering lectures. Before I hand over my session to Professor S.K. Prasad, who will be the chair of today's plenary session, I would like to briefly introduce about him. He is a well-known personality in India as well as abroad. He has vast experience. For the sake of convention, I'm just briefing. Dr. S.K. Prasad is the professor and head of Department of Civil Engineering at Vidya Vardhaka College of Engineering, Mysuru. He is having over 35 years of teaching and research experience. He obtained his bachelor degree in civil engineering from the University of Mysuru, securing first rank in 1982. Master degree in Geotechnical Engineering from Indian Institute of Technology, Kanpur in 1985, and doctoral degree from University of Tokyo in Japan in 1996. He was a visiting assistant professor at Asian Institute of Technology, Thailand for January 2006 term. He has published over 160 technical papers in national and international journals and conferences, guided over 70 master dissertations, and guided 3 doctoral students. He has completed several sponsored research projects from JSS MFE, AICTE, and DST. His areas of research interest are in earthquake geotechnical engineering and in performance-based design.
Thank you, Professor Jekka.
Thank you, sir. I will introduce our co-chair, then I will hand over to you, sir. This session will be co-chaired by Dr. Indrajit Pal, I.I.T. Thailand. Dr. Indrajit Pal is assistant professor and chair in disaster preparedness, mitigation and management, Asian Institute of Technology, Thailand. Dr. Paul, having more than 18 years of experience on research, teaching, training, advocacy, consultancy, primarily focused on disaster risk governance, hazard and risk assessment, risk perceptions, participatory DRM, public health risk, GIS, and remote sensing in DRM and climate change adaptation. Dr. Paul has published number of books and research articles in referred journal, national and international journals. Dr. Paul is member of Board of Directors for the Global Alliance of Disaster Research Institute, Japan. With this brief introduction, I request Professor S.K. Prasad and Dr. Indrajit Pal to take over the session and continue. Thank you, sir.
Thank you very much, Professor Jekka. Good early morning to good late evening to everybody in different geographic areas. I'm very happy to introduce Professor Adrian Rodriguez-Marek from Virginia Polytechnic Institute and State University. Professor Rodriguez-Marek will be delivering the next keynote lecture in this plenary session for the 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. Professor Adrian Rodriguez-Marek obtained his PhD from the University of California at Berkeley in the year 2000 in civil engineering. He then joined the faculty at Washington State University, and since 2010 is a faculty member in Civil and Environmental Engineering Department at Virginia Tech. Professor Rodriguez-Marek's research and teaching areas are in geotechnical earthquake engineering with a focus on site response, and seismic hazard analysis. His major research contributions are in the areas of ground motion characterization and on the treatment of uncertainties in seismic hazard analysis. In particular, Professor Rodriguez-Marek has contributed to the development of concept of non-ergodic seismic hazard analysis, which implies a more rigorous treatment of uncertainty in ground motion in hazard analysis applications. Professor Rodriguez-Marek's work on characterization of single station standard deviation has been used in various hazard assessment projects for nuclear power plants. Professor Rodriguez-Marek has also participated in various seismic hazard assessment projects for nuclear power plants across the globe, including projects in South Africa, Spain, and the United States. And today, he is going to talk on seismic hazard analysis for critical facilities. Sir, you have 40 minutes time, and I'll remind you about 3 minutes before. Now the platform is yours. Please do go on, sir.
Thank you very much. First, I want to make sure that you can hear me well.
Yeah, you're very much audible.
Okay, well, thank you very much. It's a pleasure for me to be able to deliver this lecture. I would like to thank the organizers for working so hard to prepare a conference under these circumstances. Being a speaker, I could watch firsthand all the work that the organizers have done, and I truly commend you for putting together this conference. I wish we could do it in person, but you have done a great job in dealing with the circumstances. In particular, I would like to thank Professor Prasad for a kind introduction, and to thank Professor Jaka. We have interacted a lot during these times, and I know the effort he has invested in putting together this session. Also, I'd like to acknowledge Professor Shankar Prakash for, I know he has been instrumental in creating this conference and in bringing this conference to India. He has done a lot to help the profession, so I would like to acknowledge him. It's always a challenge to follow a presentation by Professor Stocky. I seem to have the bad luck to always be in this situation where I'm speaking after Professor Stocky, but it's also an honor, and I will try to abide by that honor. I would like to acknowledge, before I start, the fact that this presentation is really putting together work that has been done in multiple projects, mostly projects for nuclear power plants. These projects include the project in South Africa for a siting project in Thaispun, the seismic hazard assessment of the Hanford laboratory in Washington State in the USA, a project that involved the seismic characterization of nuclear power plants in Spain, a total of 6 different sites in Spain, and a project that's currently underway that's funded by the Nuclear Regulatory Commission that's looking at the implementation of site response for nuclear power plants. The results or the observations that I'm presenting today are really the outcome of discussions that have taken place in these projects. And in particular, I would like to acknowledge the contribution of colleagues that were common to many of these projects, including Julian Bomer and Peter Stafford from Imperial College, Bob Youngs from Wood Consultants, Linda Natik, who is a consultant, and Professor Ellen Radji from the University of Texas at Austin. A brief outline of my talk. I will present an overview of probabilistic seismic hazard assessment for critical facilities, and a key element of this is the concept of non-ergodic PSHA. And in order to discuss non-ergodic PSHA, we need to understand clearly the difference between aleatory variability and epistemic uncertainty. After this introduction, I want to talk about the role of site response analysis, and in particular, the characterization of epistemic uncertainty in site response, and a tool that contribution that I think it's a simple contribution, the use of logic tree to capture site response, But I think that's very important in order to be able to properly characterize the uncertainty in cyber response. And part of that uncertainty is also related to model uncertainty. So I would like to highlight some recent work that has been done to characterize modeling uncertainty. If I have to outline two of my objectives, let's say, of this talk, is they start to introduce the concept of non-ergodic PSHA and to discuss how can we properly incorporate epistemic uncertainty in cyber response into the probabilistic seismic hazard assessment framework. Okay. So the objective of probabilistic seismic hazard analysis is to integrate across all possible earthquake and ground motion scenarios. This means that we take a source, and this is borrowed from a classic from Reiter 1990. We take all sources that are surrounding a site, and we consider for each source a distribution of potential magnitude of potential earthquakes, considering the magnitude of earthquakes that can occur at each source. For each combination of source and distance from the site, we predict ground motions, which is the third step, and we predict ground motions as a function of distance, and then we integrate all possible scenarios. And when we mention scenarios, we mean magnitude and distance, and all possible ground motion scenarios that can occur for each magnitude and distance earthquake. We integrate them to predict a probability of exceedance of a given ground motion parameter. Typically, we deal with mean annual probability of exceedance. The key element of this is that we need to account for all sources of uncertainty. And the sources of uncertainty can be grouped into aleatory variability that deals with inherent randomness and epistemic uncertainty that deals with lack of knowledge. The integration can be formulated using this classical equation, the hazard integral. We predict the mean annual rate of exceedance, which is the hazard. This is what we call the hazard for a given ground motion parameter. And for example, I will use spectral acceleration at any given period. And this is equal to the annual probability of exceeding a spectral acceleration. The integral takes into account all the natural variability of the earthquake phenomena. The probability distribution function for magnitude and distance accounts for all possible combinations of magnitude and distance that can occur that are related to the inherent randomness of the earthquake phenomena. Because it is inherent randomness, this integral, the hazard integral, is capturing the aleatory variability, the inherent randomness of earthquake occurrence. This element, the probability of spectral acceleration exceeding a certain value, is obtained from a ground motion prediction equation and captures the aleatory variability in ground motions. That means that captures the inherent randomness in ground motion predictions, and it must include local site effects. So a lot of what I'm going to be talking from now on is going to be related to how can we capture the local site effects in this integral. The outcome of a PSHA, in which the objectives of the PSHA is to develop a hazard curve for ground motion parameters, in particular, when we're talking about nuclear power plants or critical facilities for spectral accelerations, for a range of oscillator periods. And so here we take a typical range of oscillator periods, and for a range of return periods. So the lower we go here, the more rare the ground motion is, therefore the higher the intensity of the ground motion. And in doing so, again, we need to account for all sources of uncertainty. And going back to this, the sources of epistemic uncertainty are, the sources of uncertainty are divided into epistemic uncertainty and aleatory variability. Epistemic uncertainty, this comes from a Greek word, epistemos, that means knowledge, relates to the lack of knowledge. So it's uncertainty that results from lack of knowledge. And because of that, and this is the key for epistemic uncertainty, it is uncertainty that can be reduced with additional data or with further knowledge of physical phenomena. On the other hand, aleatory variability is a variability that's presumed to be intrinsic randomness of a phenomenon. In fact, it comes from the word alea in Latin, which means dice. It's related to that random nature of throwing a dice. In principle, aleatory variability cannot be reduced with additional data because it's inherent randomness. However, additional data can help constrain its value. Separating the two sources of uncertainty is important because you can identify which uncertainty can be reduced if we invest more in the problem. We add additional data or we improve our knowledge of the phenomena. So in fact, this is an important premise of my whole talk, that the distinction of these two uncertainties is important because it allows us to identify where we can improve our understanding of uncertainty, where we can reduce uncertainty. Aleatory variability is captured in the hazard integral. For ground motions, including side effects, this is captured in the ground motion prediction equation, which is implicitly included in the integral, in the hazard integral, in the calculation of probabilities of exceedance of a ground motion parameter. Now, again, this has to include side effects. So the aleatory variability in side effects has to be included in the prediction of these probabilities of exceedance. Epistemic uncertainty. And I have to say one thing. I have reviewed multiple seismic hazard assessments that are done at different levels. When we are working in critical facilities, in fact, regardless of the degree of sophistication of the seismic hazard analysis, aleatory variability is always included. Everybody that has done a PSHA has dealt with the hazard integral, therefore implicitly has accounted for aleatory variability. Not so with epistemic uncertainty. In critical facilities, we take a lot of care of accounting properly for epistemic uncertainty. But I've seen many projects, seismic hazard assessment projects, where there is no such care placed in capturing the epistemic uncertainty. However, it is a key requirement that we must properly capture epistemic uncertainty. And this implies uncertainty that can result from multiple interpretations of available data. Epistemic uncertainty may be present because the data set is not full and it doesn't sample well all the source path and side factors that influence ground motions. Or epistemic uncertainty may exist because some of the scenarios that control hazard do not have a good representation in the ground motion database. Typical way, or the typical approach to account for epistemic uncertainty is to use logic trees. So logic trees present, this is a sample logic tree for source characterization, or actually both, for source characterization and attenuation, dated 1992, but it accounts for possibilities for the different states of nature, if you wish. Okay, so you can have a source geometry that can be long or short. There is a truth, there is a true source geometry, but we don't know. It is a lack of knowledge, and we represent these uncertainties in a logic tree with weights that represent what we think is the most likely, or what's the likelihood that each of these branches represents a true state of nature. So when we do represent the epistemic uncertainty in the resulting hazard, this is represented in fractals. So you have fractals that spread out 5 to 95. A fifth fractal is one that is likely to be exceeded only 5% of the time. 95th fractal is one that's likely to be exceeded only 5% of the time. Often you don't see these fractals. It has to be only sophisticated analysis that see these fractals, but they are important because the fractals represent our uncertainty in the hazard. Typically, what we see is the mean curve. However, the spread of the fractals does affect the mean curve as well. What you see here is typical. At low return periods, at high return periods, the mean hazard corresponds typically to the median fractile. But as we go to low return periods or more rare motions, the mean hazard shifts towards the higher fractals. So a higher spread of fractals also implies a shift in the mean hazard, which is what we typically use. Also noting here that aleatory variability impacts ground motion in the slope of this hazard curve. Therefore, it tends to impact more on the on low annual frequencies of exceedance. Okay. So slope reflects aleatory variability, the range reflects epistemic uncertainty. So a question, and a very important question, is how do we identify what is aleatory variability, what's epistemic uncertainty? And it's not an easy distinction unless the distinction is made within the confines of a model, so within the confines of a parametric space. And this was very nicely stated by Professors Derkjuregen and Professor Ditlevsen in their book. It is the model builder's responsibility to make the distinction between these two types of uncertainty. So if we think about ground motions, which is what concerns us, we know that ground motions are affected by source effect, path effects, and site effects. And these elements are what contribute to source effect for geometry, slip distribution, slip time function, etc. For path, we can look at the velocity structure along the path, attenuation structure, heterogeneities that occur, Moho bounds that affects ground motions. For size, we can look at impedance, damping, and resonance effects. These are affected by layering or by the 2 or 3D structures of the soil, material properties that Professor Stocky has elaborated on this, or the depth of the elastic hull space. But the key is, how do we take all these effects and parameterize? When we develop predictive models for ground motion, we postulate these models within a parametric space, but they have to be parameters that are predictable for future earthquakes. Variations of source site and path that are not included in the parametric space, they become part of the aleatory variability. However, variations that are repeatable, variations in source path and path that are repeatable, but not included in the parametric space, should be epistemic in nature. Because of the fact they are repeatable, they should be predictable. And again, the definition of epistemic uncertainty is that these are predictable uncertainties. So if we look at the source, for example, as an example, we have all these factors that influence the source. However, our models for predicting the source include a parameterization that's relatively simple: magnitude, fault type, deep, rupture width, depth to top of rupture. So we know, for example, that stress drop has a strong influence on the amplitude of ground motions. We know that slip distribution has a strong influence on the spatial variability of ground motion. Yet these are not included in our predictive models. So any variability that results from variabilities in stress drop slip distribution are part of the aleatory variability. The same can be said of path. Our parameterization of path is simplified into distance measure of whether we are in a hanging wall or not, or whether we are in the back arc or fore arc of a subduction region. Therefore, any variability that results from parameters that are not accounted in our parameter space goes into the aleatory variability. And for a site, it's the same. The site is complex, can be extremely complex, but our parameterization is typically only 1 or 2 parameters. So in fact, these top 2 parameters, VS30 and Z1.0, are the only parameters in the parameter space of the prediction of site effects in modern ground motion prediction equations. Everything else will go into aleatory variability unless they are repeatable. And this is what I want to focus on. So what are those repeatable effects in site response that shouldn't be part of aleatory variability? And that depends on how the site response is accounted for. There are really 2 conceptual approaches. One approach that has been called ergodic, and I will explain why is it ergodic. It uses the parameterization space from the ground motion prediction equation. So it uses VS30 and depth to 1 kilometer per second, for example, to fully, as these are proxy variables that are meant to fully capture site response. It assumes then that all sites with a similar parameterization are identical. Therefore, any variability within this parameterization goes into the aleatory variability, and we compute this aleatory variability, we parameterize it with the uncertainty in predictions. But because of this, the variability is mixing space with time, because all the variability from sites that are identical in this parameter space in the network gets put into the aleatory variability, the spatial variability. But predictions at a given site over time get put together in the same bucket where we compute the variability. And this is why this is called ergodic assumption, because ergodicity, the concept of ergodicity is that the spatial and temporal variabilities are similar. An alternative approach is a site-specific approach where we presume, or we assume from the beginning, that the site response is site-specific, and we use either analysis, or if in the rare cases that we have data, we use data to predict those repeatable site effects. Therefore, the aleatory variability should only reflect variability over time. This is what we call the single station sigma. And this is what's properly called a partially non-ergodic approach. We are removing ergodicity in site response across a network, and we are computing only uncertainty at a given station. Okay. So we are back to the question, what are the repeatable effects on performing site-specific analysis? And it's actually useful to go back to how we define ground motion prediction equations. A form of a ground motion prediction equation would have a ground motion parameter, let's call it y, typically spectral acceleration. That's a function of predictive variables, which can be magnitude, distance, VS30, etc., and some model coefficients. And this will be equal to some median model that would include site response for whatever parameterization we have in the GMP, in the ground motion prediction equation, and some residual. The residual itself is typically partitioned into a between event term and a within event residual. The event term will correspond to the average residual for a given event, and the remaining residual is a within event residual, which actually can be partitioned further into a repeatable site term and an aleatory variability. And it is this repeatable site term, this delta S2S, the one that we aim to predict in site response analysis. So which are the effects that are going to be repeated event over event at a given location? If we apply the variance operator to this residual component, we get the components of variability, the between event variability or tau, the site-to-site variability of phi, and the remaining variability, which correspond to the remaining residual, which is what we call the single station phi. In an ergodic approach, all these components of variability are taken together to make up the aleatory variability. Whereas in the partially non-ergodic approach, because we predict the site term, so essentially we are predicting this delta S2S, when you take the variability of a deterministic term that you are predicting, that variability goes to 0. So the single station sigma eliminates this source of uncertainty, and therefore is made up only of the between event variability and the single station phi. So we are reducing uncertainty, but it's really not a reduction in uncertainty. It's a shift in uncertainty from aleatory, the site-to-site variability, to epistemic, because very important, we need to predict the uncertainty in predicting the site. Okay. So why would we do this? The obvious answer is because we have lower values of aleatory variability. In fact, this is research, this is from a publication that, from 2011, where we look at single station estimates of, here I'm looking only at the phi component, at various locations, California, Switzerland, Taiwan, Turkey, Japan. I'm also adding estimates by Lin that were done on a network in Taiwan. All these values are significantly lower than the ergodic counterpart. This is from a data relationship, but it hasn't changed much in that data relationship by Chu and Yang. And in fact, the uncertainty in phi, the uncertainty of the within event variability goes from an ergodic value of 0.6 to about 0.45 to 0.4 for single station sigma. So it's an important reduction in aleatory variability, which means for low return periods, you get much lower ground motions. But because another reason to do this is because if you are doing site-specific analysis, you are predicting the site term, then therefore and you are predicting the uncertainty on the side term, if you don't use single station sigma, then you are double counting uncertainty. So it's important to be aware of this to avoid inflating the uncertainty. Now, we are using lower values of sigma, which gives us lower ground motions and low return periods, but this comes at a cost. We must fully capture the epistemic uncertainty in the side term. So capturing this epistemic uncertainty in the side term becomes very important. So again, we'll go back to what are the repeatable effects. In the ergodic case, we capture the uncertainty in the side term. The epistemic uncertainty in the side term is implicitly phi S2S, is the variability of the side terms across the network. In partially non-ergodic, we must capture what is the epistemic uncertainty in each of these components that we use to predict side response. Okay. I can summarize then the role of side response in PSHA as predicting what is the repeatable side term. In fact, predicting what is this site-specific deviation at the site of under analysis from what would be the predictions of a ground motion prediction equation. We can do this two ways, using recordings, which almost never happens. It's very rare that you will have sufficient recordings to capture that at the site for a range of magnitudes that are of interest for hazard. Although it's possible, you can select study sites where this is the case. What you can rarely do is that these sites would be sites that are of interest for the placing of critical facilities. But nonetheless, it's theoretically possible. We can use predictions as a function of site characteristics. If we use predictions, it's important that these predictions include the epistemic uncertainty in the site term, which can be, if you're using recurrence, it's simply statistical uncertainty. With predictions, you have to properly account for all sources of uncertainty. You can see the estimation of the epistemic uncertainty in the site term as the cost of reducing the sigma. So this will be the cost of doing a partially non-ergodic PSHA. And one thing that I would like to highlight is that site response goes beyond what we geotechnical engineers traditionally think of site response, because it relates to all the effects that are not captured by the path in the GMP, which means that typically it goes to much larger depths, because there is variability at depth that's also impacting the site effects. And also important, what we are doing is a relative site response, relative from the target to the host, the target being the site under analysis, the host being the site condition that would be characteristic of the ground motion prediction equation model that we are using. So our site response would be a relative site response between the target and the host. Okay, so what is the epistemic uncertainty in site response? So how can we capture it? No. Again, if we look at the uncertainties that we have to consider, we will have now uncertainties in the host profile that relate to the properties of the host profile. We'll have uncertainties in the target profile that include the profile, the VS profile, density, small strain damping, usually estimated by the attenuation parameter kappa. Uncertainties in the nonlinear behavior and the modulus reduction and damping curve. If Professor Stocky were still listening, he would be very much interested in this, because he has contributed significantly to the understanding of the nonlinear behavior of soils. It's uncertainties in how we account for spatial variability in randomization, and there are uncertainties that are related to the simplification of going from a multi-dimensional problem to a one-dimensional problem. There are also model uncertainties, and we have to make a choice between doing modeling 1, 2, or 3D. We have to make a choice between modeling approach, where it's equivalent linear or nonlinear, using a random vibration theory versus time series analysis, and we need to account for model bias as well. So if we focus on the uncertainty related to the target profile, We have a challenge because it's not clear how to separate aleatory versus epistemic variability. If you choose a site, the site is not a point, it has a spatial extent. And over the spatial extent, there will be variabilities in the velocity profile. If you are simplifying this into a one-dimensional model, then even if you knew exactly what the three-dimensional profile is, there will still be variabilities that are related to spatial variability. In nuclear documentation from the Nuclear Regulatory Commission, there is a document that came out in 2013 that specifies that spatial variability within the scale of a nuclear power plant site should be treated as aleatory variability. So this is randomness in the sense that a wave that's propagating through the site will sample randomly this spatial variability. Whereas epistemic uncertainty should reflect lack of knowledge on the profile. The same document, which is important because it has been used a lot in the nuclear industry, has a recommendation for epistemic uncertainty, and it is to treat epistemic uncertainty as alternative base case profile. And this is a common sense approach that's often also done in typical geotechnical practice. And I will expand on this. Aleatory variability will be modeled through randomizations of a velocity profile around this base case profile. And let me expand on the base case profile. Let's pick this sample site where let's say our best estimate of the velocity profile is shown as a green line. We have a sand over rock, we have velocity measurements, we estimate that there is a gradient between the sand and the rock. The rock is over a much stiffer basement rock. However, we have uncertainties on the profiles, and a typical approach is let's bound these uncertainties and let's create an upper bound profile and a lower bound profile as shown in here. And typically, these are scaled to account for the uncertainty in the measurements. And if you do site response analysis for these profiles, you will get uncertainties, you will get amplification factors with respect to the base that look like this. But note, you can identify points where these amplification functions are crossing. These crosses would imply that if we use only these profiles to account for epistemic uncertainty, at this oscillator period, the uncertainty, the epistemic uncertainty is reducing to 0. But this is not real. This is simply an artifact of using a discrete number of velocity profiles and characterizing the uncertainty simply through shifts in the velocity profile. You can construct cases where, as the uncertainty increases, the hazard decreases. This was done by one of my PhD students. You have here a low and a high epistemic uncertainty case, and with the high epistemic uncertainty case, your modes spread out more, and as a result, you end up smoothing the amplification peaks, and you can end up, if you convert it into hazard, with lower hazard for high epistemic uncertainty, which is counterintuitive. You say, okay, the less I know, the lower my hazard would be. An alternative approach is to be much more rigorous in characterizing all sources of uncertainty in the velocity profile through a logic tree. We do this already for source characterization, or for ground motion models. We should do it as well for site response. This means that you account unseparated for uncertainty in velocities in the soil. These uncertainties are typically uncorrelated with uncertainties in the velocity in the rock. Okay. You may have uncertainties, let's say, in the thickness of different layers, or you may have uncertainties in the damping or in the modulus reduction and damping values curves that you use for the soil. If you could also include host profile uncertainty, because remember, we must do site response relative to a host profile. If you do this and you do site response analysis, now you don't have simply 3 curves, but you have a family of curves, typically in the order of hundreds of thousands, which are represented by the gray lines in here. And after you do this, you sample this uncertainty, but no longer sampling it in the parametric space that is input to the site response analysis, but now sampling it in the amplification function space. This resample uncertainty captures now all the range of amplification function or side response that is represented in the side response logic tree. But the key difference here, because the concept is simple, and probably many of you have used a logic tree for side response, but the concept that I'm trying to push or I'm trying to emphasize here is that we are resampling the uncertainty on a space of amplification function rather than on the parametric space that is input to the side response analysis. So we do this sampling on amplification function space rather than what typically is done in shear wave velocity. And you can do lots of neat things with this approach. You can create what's called tornado plots. These tornado plots take different branches of the logic tree and compute conditional means for each of these branches. And then you plot the resulting hazard for each of these branches. And you can sort these from higher variability to lower variability, which helps identify what's contributing most to uncertainty. For the sample that I showed before, at low oscillator periods, what contributes more to the range of uncertainty is the uncertainty in small strain damping, followed by the uncertainty in the soil velocity. At 1 second, damping doesn't have as much of an influence, but the uncertainty in the velocity, in the shear wave velocity of the soil, has the biggest contributions to uncertainty. Another way of looking at it is variance contribution. This comes from a different example, but this tells you which branch or which node of the logic tree is contributing most to uncertainty. In this case, we had uncertainty in the method used for side response analysis, or in the profile, in the velocity profile, or in the transition from the surface to deep velocities, shear wave velocities at depth, etc. Kappa is uncertainty in damping, and you can see for different frequencies what contributes most to hazard. For example, in this particular case, if you look at high frequencies, uncertainty in kappa, which is damping, has the biggest contribution. If you look at low return periods, let's say at 1 second, now the biggest uncertainty is on the uncertainty, the biggest contribution to uncertainty is on the VS profile. So you can use this approach to understand your problem better. Okay, one important additional contribution to epistemic uncertainty is the uncertainty of in model error. So the basic assumption we do in side response analysis, typically, at least we geotechnical engineers do, is assumption of one-dimensional wave propagation. We have vertically propagating, horizontally polarized shear waves. You have horizontal layers of infinite extent, and you have the base of the profile is a fully absorbing boundary condition. So it's an elastic half space. Okay. This is typically in our 1D approximation, but these assumptions are not always realized. There is parametric uncertainty in all the input parameters, and there is uncertainty in the simplification to 1D side response. Mm-hmm. When we do the side response logic tree, we capture parametric uncertainty. However, we know there is also uncertainty related to the model. This is typical. This is the epistemic uncertainty implicit in logic tree. This is from a particular project, but this is typical. At high oscillator frequencies, the parametric uncertainty leads to high epistemic uncertainty or the implicit uncertainty in the logic tree. At low oscillator periods, it does not. But we have evidence that there is uncertainty also at long periods. If you look at networks that have surface and borehole recordings, such as the KickNet network in Japan, you can see that at low periods, you have large side-to-side variability. You also can infer this from studies of downhole arrays. And that's because of model error. So how do we incorporate model error? There's two ways that we can do it. We can add model error as an additional uncertainty component. That means an additional branch in our side response logic tree. But this implies that the model error is uncorrelated from all other sources of epistemic uncertainty. The second alternative is you impose model error as a bound, as a minimum bound on the epistemic uncertainty, which accepts the correlation between the estimates of model error and the parametric uncertainty that's embedded in the logic tree. So this means that you impose a minimum epistemic uncertainty, which means that your range of fractals from the hazard that you sample from the amplification function has to be spread out to reach this minimum level of epistemic uncertainty. What is this minimum level of epistemic uncertainty? One estimate can be made from looking at the KICnet network in Japan, where you have surface and borehole records. And the borehole records are typically very stiff material, where if we were to use one-dimensional side response analysis, would predict no amplification. Yet the variability from site to site is about 0.22 ln units. So this is an indirect estimate of what the model error is. A more direct estimate can be done using downhole arrays, and different people have come up with different estimates. A recently published study by John Stewart proposes a model that's here shown in dashed lines using downhole arrays. A separate study, unpublished by Walt Silva, proposes a much lower model error of about 0.1 in ln units. Recent work by one of my PhD students has taken look at this problem using the KICnet array, and rather than using surface to borehole ratios, we use the side terms in a prediction equation, in a ground motion prediction model, and we use a Bayesian approach to obtain model error. The results are a function of how much parametric uncertainty we assume. For reasonable values of parametric uncertainty, we get these orange curves. And just to highlight here, these orange curves are much lower than the model by Afshari and Stewart that I mentioned before. And in fact, the value average across periods is about 0.22, so consistent with what we obtained in the KICnet study. So to conclude, because I know I'm close to my 40-minute time limit, side response logic tree is meant as a way to capture epistemic uncertainty in side response, and it should include all sources of epistemic uncertainty. You can use visualization approaches like the ones I showed to trim out branches of the logic tree or nodes of the logic tree that don't contribute to uncertainty. The weights in the logic tree should reflect the analyst's confidence that the given value represents the true value. And importantly, we should account for model error either as a minimum epistemic uncertainty or as an additional branch of the logic tree, and a stable estimate of model error. An average estimate is about 0.22, although it has variations with frequency that should be accounted. With this, I conclude my presentation. Again, thank you very much to the organizing committee. And as Professor Stocky mentioned, we don't do this in a void. So I also extend my thanks to multiple graduate students that have worked with me over the times in developing this work.
Thank you, Professor Rodriguez Moraik. Yeah, open for questions. And I request the audience to put your questions in the QA box. And if any of the panelists do have questions, please do ask.
There is a question in the chat box. In the chat. The question is related to the convolution approach. Should we consider full sigma for the bedrock reference hazard or remove the side-to-side component? The answer is not straightforward because, okay, you should remove the S2S component. You should consider single stage sigma, but in that, if you do that, your median estimate of the side response has to be computed, and the epistemic uncertainty should be computed as well. If you are not doing this, it means that you are computing your mean side response effects using a GMPE, and your epistemic uncertainty is your S2S. So if you're not entering additional information in a side response analysis, then you should use the full sigma, including the S2S. Now, but if you are putting additional information, then you should remove the S2S, but incorporate then the epistemic uncertainty in the site term. I hope that's clear, but it's a good question and it's an important question. And the key is you should remove the S2S component, but you can only do that if you're then placing or putting epistemic uncertainty in your mean estimate of the site term.
Sorry, I have a follow-up question for the answer you just gave. So when you say that we have to consider S2S in the site response, so you mean to say that we do amplification function, we fit an amplification function, so obviously we get a median site response, and then we can calculate the S2S. So you are suggesting that we have to deduct this from the total sigma and use it in the convolution approach.
Yes, I mean, if you're doing site response and you compute an amplification function, then you should also compute what's the epistemic uncertainty in this amplification function, and you should incorporate this epistemic uncertainty in your PSHA. But if you do this, then the aleatory variability that you use in your GMP should be the single station sigma.
Okay. Yeah, that answers my question. Thank you.
Okay, thank you. Yeah, any other question?
Yeah, can I?
Please, please.
Thank you, Professor. Professor Adrian, it's a very interesting presentation, and always PSHA is very tough to understand. And you started very nicely explaining the basics and all. I just have one curious question. You said when there is more uncertainty, your error parameter estimation is coming down. Okay, when there is less uncertainty, it is more. In common sense, by common sense, it appears it should be other way. So what is your take, please?
But what I said, just to clarify, is you can construct cases for additional uncertainty leads to lower hazard, which is not good. No? That's why this would result only if you are using a very crude approach to trying to capture epistemic uncertainty, meaning that you are only, let's say, using this approach of scaling shear wave velocities. You could end up with a case in which you have this pathological case of lower hazard for higher epistemic uncertainty, and that should be avoided. And we could get into philosophical discussions as to why in some cases that could be the case, but in general that should be avoided. And a way to avoid that is using the approach that I indicate, in which you are more rigorous about capturing uncertainty by using capturing all the uncertainties in site response within a logic tree approach.
Thank you.
Any other question? Yeah, please, Dr. Indrajit Paul.
Yeah, Dr. Adrian is that PSHA and DSHA is very close to my heart actually during my PhD studies, but couple of years I'm slightly changed my domain to the governance. So while understanding your domain area, I mean, it's really interesting. You're doing a lot of things on the nuclear power plant, and that is one of the critical infrastructure. And we're also working on some other critical infrastructure in the energy infrastructure, especially. So I was curious to know, like, while you are doing the PSHA and especially for the site response, and there is a large amount of uncertainty, but in case of the critical infrastructure, you had a huge amount of investment involved in selecting the site where it will be constructed. So in that context, what is your suggestion? Like, how much uncertainty we should take a risk of investing that amount of money, because any CI or critical infrastructure having a huge amount of investment. So in that context, what will be the confidence level of the model we are talking about? And the second link to that point also, while considering the seismic part, so are you also considering the maximum credible earthquake for that particular locality where we are working for the seismic velocity and the seismic hazard assessment for that particular location.
Okay. So if I interpret your question, the first part of your question correctly, is why are we using a probabilistic seismic hazard assessment in view of considering deterministic approaches in which we are considering a maximum credible earthquake? I think, well, I think there is a false dichotomy that the probabilistic approach negates or negates the deterministic approach. In reality, in a probabilistic approach, you are considering all possible earthquakes, including a maximum considered earthquake, maximum considered ground motion. The difference is that in the probabilistic approach, you are also assigning, you are weighting all those scenarios by the probability that these scenarios would occur. So the problem with deterministic approach is that you are putting essentially all your weight on a single scenario. And whereas the typical thinking is, well, this is the worst case scenario, in reality, there are possible worst scenarios that exceed that maximum credible earthquake. So in probabilistic analysis, you take into account those larger scenarios by giving them lower weight. So I will say that the primary reason for doing probabilistic approach is that it creates a rational way of deciding what level of ground motion to use. Whereas in the MCE approach, in the deterministic approach, there is a choice that's made a priori of what this worst case scenario that precludes necessarily worst earthquakes, and often doesn't account for more frequent earthquakes that by virtue of occurring more frequently can result in higher hazard. And that choice is not always made with statistical rigor. It's often based on a large degree of judgment. In probabilistic analysis, we shift that judgment to selecting what's the hazard level that we want to choose. Now, as to the second part of your question is, how do we account for uncertainty? Well, I think that's what differentiates, that's what makes for a good PSHA, how to properly account for all the uncertainty. And in critical facilities, that's done through an expert elicitation process, where the task of the expert panel is to capture what we call the center, body, and range of technically defensible interpretations. And I would claim that the best way of doing this is by trying to follow some type of rigorous expert elicitation process that involves process of evaluating all possible interpretations of data and models, and then a process of integrating all this information into a model that tries to capture all this uncertainty. And I don't know if there's a magic recipe for this, but in the US nuclear industry, there's a process called the SHAC process that postulates such a process to try to capture this uncertainty. I hope I answered your question, but feel free to send an email if you want to elaborate.
Understand why DSHA, sometimes we are considering like extreme cases, right? That's why. Yeah, thank you for the explanation. Yeah. We have few questions in the chat box as well, in the Q&A.
Just quickly to add, I have just followed. Yeah, can I ask quickly? Yeah, means if I rightly understood, like PSHA may provide in some cases maybe worse scenario as compared to DSHA. Am I right?
Yes, in some cases it does. In fact, if you look at the seismic hazard map in the US, PSHA has led for near fault scenarios to much higher ground motions than deterministic approaches. So it depends. In some cases it can be lower, in some cases it can be higher, but definitely there are cases where it can be higher.
If it is lower, should we go with the DSHA or PSHA?
I don't think so. If you have a PSHA that's rigorous or conducted, and so you can make an argument that you want to go to ground motions that corresponds to lower frequencies of exceedance. No, for reasons that are not related to the seismic hazard in itself. But if you have a target exceedance, let's say 2% in 50 years, and that's your regulatory target, because let's say you have a target, you want to restrict probability of collapse to a certain level, then I see no reason to choose deterministic approaches if they give you higher values, because those values that are the deterministic approach are giving you corresponds to probabilities of exceedance that are much lower, which it means that you are, if you have no reason to target lower probabilities of failure, then there is no reason to go for a deterministic casing.
Thank you.
I'm a strong believer in the probabilistic approach because it can lead, the choices should not be made deterministic or probabilistic. The choices should be made, what level of hazard do you want to accept? No, and that comes on the probabilistic approach.
And probably based on the level of confidence on the analysis that we are doing.
Absolutely, and that's why you have hazard fractals, and you can choose then. It's okay, if you want to be more conservative, then you don't use the mean hazard, use a certain fractal of the hazard.
I'm not there in the figure.
Thank you, Professor.
Yeah, Adrian,
Yeah,
can I ask a last question? Quick one, very quick one.
please, sir.
Thank you. Thank you. I just have a very quick question. So when are we going to graduate to do the probabilistic analysis in liquefaction?
That's a very good question. I'm gonna tout one of our own work, our own papers, but we published in 2020 a paper on the probabilistic analysis of liquefaction for the Groningen site in Netherlands. The lead author is Professor Russell Green, who is a colleague at Virginia Tech, where we have done a very rigorous probabilistic analysis of liquefaction. So I think we are there. It's just that it's not a common approach yet, but I think we should start doing it. I think we have the tools. We have demonstrated in Groningen. I think that was a very nice study, that a publication in the Journal of Geotechnical Engineering of I.I.Sc. But I think we should move that way.
Yeah. Thank you. We have started that. That's why I asked that question. Thank you.
Okay. Yeah, if by chance there is no other question, maybe we already have exceeded our time. Therefore, I request Dr. Indrajit Pal to summarize. And from my side, I thank the organizers. We had 2 excellent lectures. I felt really honored to listen to both these lectures. And thanks to the organizers for giving us the opportunity to listen to as chairpersons of the plenary session. And over to Dr. Indrajit Pal to summarize and end.
Yeah, thank you. I think it's a nice discussion in both the cases, like for Professor Adrian and also Professor Kent. So we had 2 different dimensions. We have listened from 2 experts, and the second one right now, Professor Adrian, also we have nothing to elaborate too much, because we discussed also a lot on the PSHA, especially the probabilistic seismic hazard assessment. That's one of the sort of discussion. And right now, I think most of the countries having almost need and some extent develop a certain resolution of PSHA but I think still there is a lot of work to be done on the microzonation using the PSHA for many of the seismic active countries. But I like 2 extremely 2 interesting factors where Professor Adrian mentioned about the 2 different approaches for the uncertainties, and also the decision tree. And lastly, the discussion also ended up with the possibility with the intervention of Professor Sitaraman, like how we can expand this activities to the PSHA towards the liquefaction. We also believe, and there is also discussion with the PSHA and DSHA, what is good and what is bad, but I think both are the things important, and we had a different dimension for both the approaches. So with this brief, I'd like to thank both the excellent keynote speaker, and also thanks to the organizer for inviting these excellent speakers and as well as a nice discussion. Thank you so much.
Thank you very much.
Thank you, Professor S.K. Prasad and Dr. Indrajit Pal. On behalf of organizing committee, we thank you both for nicely conducting this session. And we also thank Professor Adrian and Professor Stokoi for taking out their time in odd times and making presentation. It's really very wonderful and educative. Thank you one and all. I request Professor Sitaram, Chairman, if he want to say any final concluding remarks.
No, thank you. I think every session I should not come. It's all right. So but first of all, thanks to both the speakers, Kenneth Stokey as well as Adrian, for an excellent lecture, and I really enjoyed, and also very lively discussion. And I started liking this platform so that I know I can do my work also as well as listen to lectures. Thank you so much. Namaskar.
Thank you one and all. See you all tomorrow morning.
Thank you.
Tomorrow morning,
Bye-bye.
yoga. Sorry. Tomorrow morning, those who are interested in yoga session will start at 7:15 in the plenary hall. Okay, please join.
Thank you.
Thank you.
Like
Thank you.
And tomorrow evening, 6:30 is the cultural program, which will be a sort of a really a retreat of Indian culture, particularly Bharatanatyam and also Hindi songs, which is Bollywood. And in addition to that, there are some children also playing some dances and programs. Thank you.
Thank you. Thank you so much.
Thank you.
Okay.
Thank you.
Good night.
Yeah. Thank you, everybody.
Thank you, everyone.
So, Ravi, are we joining on the other link?
Yes.
Yes, sir.
All join, sir.
Yeah, we'll join the other.
Thank you. We will leave and rejoin on the other link. Thank you.